did you know that a pebble that can easily fit on your palm can destroy a 200-ton spacecraft? Actually, even that is an exaggeration. You only need a speck of paint, which is often too small even to be seen with the naked eye, to cause serious damage to the delicate instrumentation on a satellite. In fact, the risk is so great here that NASA actually did something called a hypervelocity test. In this test, they will take small objects weighing a few grams and send them careening into obstacles at extremely high velocities. In fact, this is one such test. You can see that the impact has completely vaporized the target. So it's now a gas. So clearly the problem is important enough to spend a lot of money over. The question is, why can a speck of paint cause this much damage to a spacecraft? And this is the question we will be able to answer today once this session is over. So why do these space stations and spacecraft face so much risk from flying objects? The answer is in kinetic energy. So let's begin with the definition of kinetic energy. It is the energy possessed by an object by virtue of its speed. So it is the amount of work an object can do because it has a speed. Please remember, we are talking about speed here, not velocity. And the reason for that will become clear pretty soon. 65 million years ago, an asteroid the size of Mount Everest plowed into the Mexican region of America. And the impact completely wiped out the dinosaurs and is in fact an important reason why we are here. This asteroid was traveling at more than 10 kilometers per second, and that was the reason it was able to carry so much energy with it. Now, how do we quantify this energy? How can I know how much energy was delivered by this object to the Earth due to its speed? Let's try to derive this with a slightly more down-to-earth example. So here we have some gentle raindrops falling on the ground. So the raindrop has some mass, and because of the influence of gravity, it is falling towards the Earth. So let us focus on this raindrop. It has a mass of m, and it is under the influence of the gravitational force. We know that energy is the product of force and displacement. So we have a relationship here. W, that is work or energy, is equal to F of S times delta S. Now what is F of S? It is the force being exerted on this object, and we say F of S because in case it might have a dependence on the displacement from the ground. Delta S is the change in displacement. It is the distance that the drop is moving vertically. We know that force can be given as mass multiplied by acceleration. How do we use this result to find the answer we require? Well, we have already found that change in energy is equal to the work done. So here it is F of S multiplied by delta S. We can consider F of S to be constant here because for this case there is no significant change in the force of gravity as the drop moves from its original position to the ground. Now delta W, that is the change in work or the work done, is equal to F of S, which can be written as mass multiplied by acceleration times delta S. So we have a new relationship. Work is equal to m times a times delta S. Now what is a? It is acceleration. We know that acceleration is the time rate of change of velocity. So we can rewrite this equation as delta W is equal to m times delta V by delta T times delta S. So what is this term here? It is simply a substitution for acceleration. It is delta V by delta T, rate of change of velocity per unit time. Now we play a small mathematical trick here. I will shift the delta T in the denominator here to here. So we can rewrite this equation as delta W is equal to m times delta V multiplied by delta S divided by delta T. Mathematically, this is completely normal. The reason we did this is, if you look at this equation, delta S by delta T is the rate of change of displacement with respect to time. And we know this by a different name. We know that delta S by delta T is actually the definition for velocity. So we can again rewrite this previous equation in this form. That is delta W is equal to m multiplied by V multiplied by delta V. Now, if we calculate the work done over tiny increments of displacement and we add all of them up together, we will find out the total change in the object's energy, which is the change caused by the movement of this object, by the kinetic nature of this object. So that gives us the relationship work is equal to m multiplied by the integration of v dv from 0 to v. If you perform this integration, we come across our familiar equation, that is work done or the kinetic energy of this object is equal to half times m times v squared. So what do we learn here? The SI unit of kinetic energy is joules or J. So it is measured in exactly the same way as any other form of energy. The dimensions of kinetic energy are m to the power 1, L to the power 2 and T to the power negative 2. You may recall that this is the exact same dimensional relationship for any other form of energy. Let's verify if this is true. We look at the equation for kinetic energy, that is half mv square. So clearly the dimension m is for mass, that is capital M. And if we take speed squared, that is L t to the power negative 1 whole square, that is L to the power 2 t to the power negative 2. If you multiply these two, we again come to the familiar dimensional equation, that is m L square t to the power negative 2, which verifies that kinetic energy is exactly the same as other forms of energy in its behavior. These dimensions are the same as that of gravitational potential energy and elastic potential energy. So it is measured in exactly the same way. It has the same units. It is the same thing. So Ke is equal to half mv square. This tells us that assuming that the mass of the object is constant, kinetic energy is proportional to the square of velocity. So if an object is moving at a velocity, let's say 10 kilometers per hour, and it accelerates to 20 kilometers per hour with no change in its mass, we realize that the velocity has doubled, which means that the kinetic energy of this object will not be doubling. It will be increasing by the square of 2, that is 4 times. So doubling the speed of the object has increased its energy by a factor of 4. If I were to increase the speed of the object by 3 times, let us say we went from 10 kilometers per hour to 30 kilometers per hour, the energy of this object would be increased not by 3 times but by the square of 3 times, which is 9 times. So we realize that the energy of the object increases very quickly with an increase in velocity or speed. Please also remember that this is a scalar quantity. So the velocity of the object does not really indicate the energy that it has, because an object could be traveling in any direction at a given velocity and still have the same amount of kinetic energy, since it is not a vector quantity. So coming back to the original question, how can a tiny speck of paint cause this to happen to a spacecraft? Remember that this tiny speck of paint, and I cannot emphasize this enough, it weighs less than a fraction of a gram, is traveling at a speed of over 8,000 meters per second. At this velocity, it has a huge amount of kinetic energy, which is what causes this to happen. So, in order to protect against this kind of collision, it is very important for engineers to keep track of all the junk which is floating around in space. So this is actually a major issue now, because in the old days there were not a lot of spacecraft and satellites, but now we have Iridium, we have Starlink, we have new missions all over the place. So this has become a very real concern because of the sheer velocity, the speed at which these objects are moving with respect to each other. So to summarize what we have learned so far,
Manorama Horizon, learning made simple.